The last topic we're going to discuss in this unit is multi-stage amplifiers. So for most applications, a single transistor circuit is not going to be able to meet all of the specifications. So we're going to have specifications for our gain, our input resistance, and our output resistance. And again, we're going to need to consider our input and output resistance because in real applications, our loading effects are going to be very critical. So the solution to this is, of course, to have several transistor circuits connected together. So our solution is several transistor circuits connected together, which we can call multi-stage amplifiers. And so what we can think of this as is, maybe one stage is primarily responsible for our gain, but maybe it doesn't have the right output resistance, so we need to have another stage to give us our appropriate output resistance. Similar thing for our input resistance. So we can sort of take the best qualities of all of these, and if we connect them in the right way, we can sort of take advantage of that. And so in the textbook, we're not going to go over it in detail, but section 6.9, so section 6.9, which is on page 436 in the textbook, talks about a few different connection types that we can use. We can have cascade connection types, we can have cascode connection types, and we can have something called a Darlington pair. And so I want to briefly mention and look at this Darlington pair, just because I think it's important that you guys are at least aware of it and sort of the basic structure. So let's do that real briefly. So the basic sort of improvement that our Darlington pair gives us is increased current gain. And so in this simple configuration below, we can see that because we have our emitter of Q1 connected to the base of Q2. And so what we can think of as our base current into Q1 is getting amplified by beta, and then that is getting amplified by another beta. So essentially we're going to have sort of two betas, or beta squared, for our overall current gain. A couple other things to point out about this circuit is we notice that we have this current source, i.e. Q, which is biasing our transistors in the appropriate region. And so we're going to come back in another class and talk about how we can construct that current source using more transistors. We also notice we have a bypass capacitor CE on the emitter for Q2. We notice that the two collectors are connected together here, and that's defined as the output. And of course we have our input over here on the left, where I've neglected our source resistance in this case. So one thing I want to do too is sort of go through the process of how we would create a small signal equivalent circuit when we have more than one transistor. And so what we're going to do is sort of take the same approach we have before and start by writing our base collector emitter terminals, filling what's in between them, and then connecting the external circuit. The only difference is now we're going to have to do that twice, once for Q1 and once for Q2. So to get some practice with that, let's go ahead and do that for this simple circuit. So for our Q1, we of course are going to have a base, a collector, and an emitter terminal. And because we have the two Qs, or two transistors, let's distinguish that by B1, C1, and E1. So between our base and emitter, we're going to have our emitter resistance R pi, and that's going to be R pi 1 because it's going to be different than our value for our Q2, and that's going to have some voltage V pi 1. Between our collector and our emitter, we're going to have some dependent current source. Because it's an NPN, the current's going from collector to emitter, and so this is going to be GM1 times V pi 1. So all of these parameters now have to have subscripts to distinguish them from the parameters for Q2. In this case, let's neglect our early effects, so we're assuming that our R0 is infinity. All right, so let's do the same basic thing for our Q2. And I'm going to place these three nodes sort of strategically, noting that our E1 is connected to B1, so knowing that, E1 is connected to B2, so I'm going to put my base 2 right here so we can easily connect that to E1. We note that the two collectors are connected together, so I'm going to put my collector C2 up here to easily connect those two collectors. And we see our emitter 2, because of that bypass capacitor, is connected to ground. So I'm going to put my emitter 2 sort of down here so we can put that on ground on the bottom. All right, so now between my base and the emitter, of course I have my R pi, but this needs to be now R pi 2, and there's a voltage V pi 2 across that. Between the collector and the emitter, I have a dependent current source with current going from the collector to the emitter. And the value of that current source is going to be GM2 V pi 2. All right. And so that would be our second transistor Q2. So now what we need to do is go back and, sorry, let me mention real quick, we're assuming again that we have an infinite small signal output resistance. So now we go back and we said, well, these two collectors are connected together. Our emitter from Q1 is connected to the base of Q2, so that's pretty easy to do. We had also said that our emitter E2 is at ground, at signal ground. We can see that our collectors are connected to signal ground through this RC. So we can come over here and add our resistor RC like this. So that's our RC. We note that our Vout is defined as a cross RC, so we have Vout defined here. So let me use my phasor notation to be consistent with the notes. And then on our base side, I'm going to make some minor adjustments. So we can do a voltage, or rather a source transformation. Again, that CC is going to act like a short circuit. So what that's going to give us is some base resistor in series with a current source. So we get something that looks like this, and this is going to be our RB, and this is going to be some input current II. And so typically for our first order analysis, at least what's shown in the textbook, they're actually going to ignore this RB as well and just focus on the input collector current. As I mentioned, we're not going to go through the analysis of this, but if we define our output current as being over here, what we find is that our current gain, our small signal current gain, is approximately equal to our beta 1 times beta 2, as we sort of qualitatively guessed just by looking at the configuration in this initial circuit.